Sweet. Hello, my name is Josh Wheeler, and in this video I will be explaining and coding a closed water and air system problem. So let's get right to it. Alright, so in this problem, we have a given container. So in this container, we are given a total volume that is in the container that can totally hold. So in this, we know that for this problem, we have a total volume that is equal to, I believe is 0.1 meters cubed. Okay? So in this container, we have two different substances. We have the water at the bottom, which we know the mass of the water to be 1 kilogram. So we know the water to be 1 kilogram. Okay? And what's left in the container, now what's interesting about this container, it was open at a certain point. So that is not completely full of just water. There's air inside of here as well. It has its own pressure just like water does, which is going to mean something important in a second. So we have air in the system as well. So now other knowns that we know. We know that the initial pressure of this system right here was equal to 101,325 pascals. Another known that we know the initial temperature of the system at the start of the problem was equal to 298 Kelvin. Now, getting on to what we were solving for. So we know that the final pressure of this system was equal to 200,000 pascals. Got a zero in there. 200,000 pascals. And what we were solving for, we want to know the final temperature, or the temperature increase that it took to reach from this initial pressure, in this, given these parameters, to reach this final pressure. So what was the final temperature when the final pressure was at 200,000 pascals? That's what we were solving for. Okay, so like I said before, there are two substances in this container, one being water, one being air, or in this case, the air is also water vapor. So we can ask ourselves, the total pressure in the system, which we are asking for right now, is, we're solving backwards, 200,000 pascals, so we can go ahead and write this out. The final pressure, or the total, which we know to be 200,000 pascals, is equal to the pressure of the water vapor, in this case air, added to the pressure of the water in the system. So we can write this out. So we have the pressure of the water, which in this case we could solve for using Antone's equation, which we did in a previous video. So we know that Antone's equation is equal to 10 to the A minus B over T plus C power. In this case, T is the final temperature which we are solving for. So we do not know this. And these are initial guesses to help us find the water pressure. Plus the pressure of the air, in this case vapor. Now we can use PD equals nRT, in this case, equation, to solve for the pressure of the air. So we can go over here and say that the pressure of the air equals nRT over V. Now, in this case, N is the total number of moles of air in the system, which does not change from the initial start of the problem to the increase of temperature and pressure at the end. So there is no change in the amount of air moles in this problem. So there is no change. I'll write this down. We know this to be 8.314 moles per joule Kelvin. And this is also, like I said before, in the water pressure problem here in the Antone's equation, is the final temperature, which we do not know. And this is the volume of air that is in the system. Now we can further go down and solve for the volume of air. We need to know this. So we can solve for the volume of the air by actually going here and doing the total volume of the system, which we know to be 0.1 meters cubed, minus the volume of the water in the system. So now we can break this down even further and ask ourselves, what is the volume of the water in the system? Well, we can do that. We can find this actually given what we already know about water. So we know that in this case, we have a mass of 1 kilogram of water inside. So volume equals mass over density. We know the density of water to be 1,000 kilograms meter cubed. So we can solve for this knowing that we have 1 kilogram of water over 1,000 kilograms per meter cubed. Okay, so using this we can find the volume of the water, which is subtracting that from the total volume. That gives us the volume of the air, and we use all these given parameters to find the total, the final pressure, which we're trying to find. Okay, so this is the final part of this we're trying to solve for. So now we can move over here. And we can ask ourselves, okay, so this is what the final pressure and final temperature is going to be. We need to do this equation again, but with the initial temperature, initial pressure. So we can do this again. So we know that the initial pressure, in this case, which was known to be, that's right here, 101,325 pascals, is equal to the pressure of the water, which again we can use Antoine's equation, to solve for, plus the pressure of the vapor, which we can do the same exact thing we did before. We can use PV equals nRT to solve for this, which we know that P of the vapor, so the pressure of the vapor, equals the number of moles, which does not change from the initial, which I can write this in your head. This is the initial, the starting temperature, the starting pressure, everything we know already. And this is the final over here. So we have the final and we have the initial, which we're working on right now. Okay, so now we can go here and say that we know that the number of moles of air does not change from both of these equations. And that's the very important part. What we're going to do here is what I want to show you is that in this case, we know the initial temperature to be 298 degrees Kelvin. We know that the R is 8.314, and the number of moles does not change from both of these. So we can break this down like we did before. We have the total volume minus the volume of the water. This is equal to 1 kilogram of water, which we already know we have, times over 1,000 kilograms per cubed. Okay. So now, knowing what we know already, we know that this is 298 degrees Kelvin. We can find the volume of the vapor, the air vapor inside. We know this is 8.314. And we can actually use all of this to solve for the number of moles. Once we find the number of moles, we can then plug that into this equation over here, our final equation, and use this to solve for the final temperature. So now that we've solved for, we know that we have to solve for the number of moles of air in the system over here. And we know that we can use the initial equation to find that, given that we already know the initial temperature to be 298 degrees Kelvin, R to be 8.314. We can find the volume of the vapor inside, given the derivative breaking down of this right here. And we can use Antone's equation to solve for the pressure of the water in the system. Okay, so knowing this, we can actually simplify and rearrange the components here to find the actual number of moles of air in the system. So we can say that the number of moles in this system equals the pressure, which we're looking for, which is going to be, in this case, for the initial problem, is going to be 101,325 pascals, minus the pressure of the water, which is at 298 degrees Kelvin, multiplied by, so let's see, we're going to multiply this by the volume of the vapor, which we can find using the breakdown right here. Okay? So multiplied by the volume of the vapor divided by the R value, which is 8.314, and multiply that by the initial temperature, which is 298 degrees Kelvin. Okay, so now that we can find N, we can actually go into our computer code in Python and actually code this out. Solve for N and plug our N value, which does not change, like I've said multiple times, into our final pressure equation. Plug N in and solve for the final temperature. Okay, so as we stated previously in our examples on the whiteboard, we have two equations given the knowns of the initial temperature, our initial pressure. We have the total volume. We know the substances inside. We know the weight or the mass of the water inside, and we know the total pressure, the final pressure. And we're trying to find the temperature at the final state where the pressure is at its final state. So in this case, the final temperature is going to be unknown, and we do know the final pressure, which is to be 200,000 pascals. Okay, we wrote up equations. We actually wrote up equation previously talking about how to solve for the number of moles of air, which does not change from the initial state, where the pressure is at 101,325 pascals, to our final state, where our pressure is at 200,000 pascals. So that doesn't change, and that is going to be a key here in order to solve for the final temperature. It's going to be our link between the two equations. So now I'm going to get to the code. Okay, so now we are going to actually import data from GitHub from, let's copy it in. And so you'll see this here. CHE Tools is a workbook in GitHub that has a bunch of different data, equations, and software that allows us, or programs, that allows us to solve for different different compounds, and different things about them, different properties, whether it's anything from vapor pressure to density to heat of vaporization, different things like that, and allow us to run multiple complex codes, programs, in order to solve for unknowns, which we have, rather than doing it by hand on a whiteboard. All right, so we're going to call this in. Make sure everything's initializing, checking here. All right, so it's called in now. So we can actually go ahead and import tools.che as CHE, and we'll give it a different name. And tools. Had a little typo there. Let's run it again. Looks to be running. And we'll take out the S here. We don't want to have that there. All right, sweet. So now that we imported this, we can actually go up here on our window, and we see here now we have called in. So what this program does at the top here, we actually have it copying this workbook from GitHub and bringing it in here. Now the import function actually brings all those data files. If I didn't do the import function, it would all be right here at the in this little window, and we can't work with it. So we have to import the certain tools we want to work with in the program. So we now have CHE Tools over here on the side. And if we go to Tools, we're going to be working mainly out of all these different programs that allow us to solve these complex equations. We're going to be mostly working with CHE.py. And you look over here, this is what I'm talking about. We have a large amount of code in here that allows us to solve for multiple different kinds of equations, variables, all these different information, which we don't have to code out and actually write out by hand, actually. So we can just call this in. It's readily available, we call it in, and we can actually work with this right away. And actually, we can look at the Data tab next. Get rid of this. We can go to the Data tab, and you see here, we have about 30 different compounds that we could possibly be working with. And in this case, we have anything from oxygen, nitrogen, methyl acetate, methanol, but mostly today, which we've been working with the problem, we're working mostly with water. So we can go to the water props text. We're going to bring this on the side here. And this file actually has all sorts of different information on the compound of water. Anything from molecular weight, you can see here, critical temperature, melting point, boiling point, anything. There is so much data in here, the different values, the units that they have, which are very important. And if we go down here to the bottom, you'll notice we actually find the vapor pressure. Now, as I've explained in a previous video, or before in the equation, the end-to-end of the equation can be used to find the vapor pressure of substances given a temperature. So you'll notice here that in the end-to-end equation, coefficients of A, B, and C can be used to find the vapor pressure of a substance given a certain temperature. And you notice there are only 3 different coefficients in that equation. But if you notice down here in the coefficients, we have 7 coefficients in this line. So what does that tell us? It tells us it's using a different equation. In this case, this equation is known as KimCAD equation 101. This means that there is more than one equation that can be used to find the vapor pressure of a substance. And actually, in this case, KimCAD equation 101 is more complex and more precise because it gives more coefficients to guess, meaning it can give a more precise answer, which we want in this case. So answer an equation, it's easier to use. It has less variables which we try to solve for and manipulate. But in this case, the KimCAD equation 101 gives us more parameters which we can manipulate, guesses, and it gives us a more precise answer, which we're going to use in this case. Okay. So now that I've explained that, we can actually go about bringing in the water data, which we're going to work with. So let's bring in a new line here. And let's do P equals CHE dot props, which in this case, props means properties. And we're going to make sure it's in brackets since it's a list. And we're going to put this in quotations. We're going to call in water. And bring in caps. All right, shift enter. All right, so you notice here, it says, it doesn't look like a lot just happened, but really what just happened, it imported all this data on the right side here in this list and brings it in here for us to actually work with. So if I wanted to bring in a new line and say I want to look up let's look up the vapor pressure real quick. Let's say we want to look up P VAP at a given temperature. We'll say the boiling point of water, which is 373 degrees. Let's try that. Kelvin. And shift enter. So it brings me. Yeah. So the boiling point of water should have about 101,325, something around that pascals. So we see it's 100,332, about 7 degree pascals off, which is pretty precise. It's very hard to get the actual 101,325. So that's very good. It's very precise, given the KimCAD equation 101. Allows us to use that. Okay, so now that we know this, we can actually bring in our values, which we already know. So we can go down here in a new line. And we do know from previous on the whiteboard, we know that our temperature initial is equal to 298 degrees Kelvin. It's in K. we know the total volume is equal to 0.1 meters cubed. We know the initial pressure to be 101,325 pascals. All right. And we know our final pressure to be equal to 200,000 pascals. All right. And let's see, what else do we need? We need to know R. In this case, R is equal to 8.314. And that is in the units of joules per mole Kelvin. So mole Kelvin. Let's see, is there anything else we need to know? We know the initial temperature, that, and that. All right. If I forget anything, I'll come back up here and write it down. But I think that's it. All right. You know the total volume. Oh, I forgot the weight of the water. Yeah, that's very good. Okay. So the mass of the water we know to be 1 kilogram. All right. So now that we know this, we can just run that and make sure the program knows it. All right, so we can bring in a line of code. So now I can actually, I'll actually demonstrate also another property we can bring up about water. We can actually look at the density of water, which we're going to need to solve for the number of moles of air in the initial equation in order to bring that over and plug that into our final pressure system at the final value of pressure and solve for the final temperature. So we can find the density of water by doing P dot rule at a given temperature, which we're going to guess at our T initial. Shift enter. Yeah, and so our density, in this case at our certain temperature here we're guessing, is at 995. That's, I believe, at kilograms per meter cubed. I believe that's the units of density. Make sure you know that density. So units. Try to make sure this is right. Yep, kilograms per meter cubed. All right, I was right. All right, sweet. So now that we know that, we've called that in. We can actually start writing out our equation for the number of moles of air in the system. Okay. So let's see. We want to say in air equals. So we know that in air is equal to the initial pressure, which we know to be 101,325 pascals, minus the pressure of the water. The pressure of the water in this case, would it be? No. Yes, it would be pressure of the water. Pressure of the water, so we can find that by doing P dot P VAP at our initial temperature. Okay. And we multiply that by the, now we're going to try to solve for, what was it? We're going to try to solve for the pressure of the air. So we need to manipulate the equation for PV equals nRT. So we need to bring that in. So we're going to try to solve for the volume of the air, which is going to be equal to the total volume, so V total, minus, now the volume, we need to subtract the volume of the water in order to find the volume of the air in the system, or the vapor in the system. So in order to do that, we need to take the mass of the air, which is 1 kilogram, divided by our density of the air. So P dot roll at our initial temperature, which we just found above. We actually put the C so it's a little more sectioned off. All right, so this is right. So that goes to here. We need one more parenthesis on the side here. Okay. All right, so we've got that divided by our R value, which is 8.314 joules per mole Kelvin, times our initial temperature. All right, and let's run it. So now if we go down to a new line of code, we can actually check what our air value is. Yep. So our new air, our moles of air in the system does not change from the initial starting point of pressure to the final point of the pressure in the system is 3.92 about. All right, so now that we've called this in, we can actually start writing our equation. So now we know this, we can actually plug this in to our function of the final pressure and try to solve for our final temperature. Okay, so let's go and bring in a new line of code. So we want to define our function. So let's say define our function. Let's say the pressure equation. So P EQ. Let's give it a variable of X. And let's go down one. So we need to unpack this. So we need to say that, let's see, our final temperature is equal to some value X of 0. So as we know in Python, the identifier is in a list. X is going to be our array. It's going to give our answer of temperature. So in this case, since we're only trying to find one unknown, it is going to give us one number in this array. And the identifiers for arrays and lists in Python start with an identifier of 0, meaning the first item of the list is a 0. So since we're only working with one variable, trying to find one part of this equation, it's fine. It really doesn't matter as much. When we get on to more complex questions and equations, when we're trying to find multiple variables, saying like we're trying to find in a next example after this, I finish this code, I will try to solve a problem where we don't know the final temperature and we don't know the total volume, but we do know the number of moles in the system of air. So I'll show that next after this. So we're trying to find the final temperature. Okay. Let's try to find the volume of the vapor. So volume of the vapor equals, okay, so the volume of the vapor is equal to, let's see, volume of the vapor is equal to the total volume, V total, minus the mass of the water, which we still know to be 1 kilogram, divided by the density, so P dot RHOL. This time we're going to plug in the final temperature. All right, does that look good? All right, subtracting that. All right, sweet. We want to find the pressure of the air. Now, what else do we need? We need to solve for the, we have the total. So now we're going to want to find the pressure of the water, the partial pressure of the water. So PW equals, in this case, we're using ChemCat equation 101. So we're going to use, let's see, P dot PVAP at our final temperature. And now we can find actually the pressure of the air, or the vapor in this case, by doing the number of moles of air, which we know, so PV equals nRT. Just mixed around a little bit, trying to solve for P. So we know the number of moles of air times our R value times our final temperature. Put that in parentheses real quick. Divided by our volume of the vapor. So we know that's V. That. Okay. So now we're going to want to ask ourselves, so how to solve for this. So in Python, or in general, for our equation, which we had on the whiteboard before, our P final is equal to the partial pressure of the water added to the partial pressure of the air or the vapor inside. So that right now by itself is good and all, but we need to solve, we need to set it equal to 0. We need to find the zeros. So finding zeros in this case, we can actually look at here an example I've already had written up. I should change this around a little bit. So let's give out an example of y equals x squared, which is a parabola. And let's bring it down by like 3. Seems to be a problem here. Oh, wait. Let's do it again. So y equals x caret 2 minus 3. All right. So see, in this case, our zeros are where it crosses the y-axis, or not the y-axis, the x-axis. These are our zeros. So we want to set our function equal to 0. So we need to, and essentially what I'm saying is we're going to bring our final pressure and bring it over to the right side and set it equal to 0. So it's going to be a negative final pressure. So we're going to, first of all, we're going to want to return our equation. So return our, so it's going to be our pressure of the air plus our pressure of the water minus our final pressure, PF. All right. So what we're going to run that. And we're going to bring in a new line here. So we're going to put root. So essentially, before we can do anything, we actually need to bring in the code or the software that's going to allow us to run this. So Python has a very nice code written out for us. So scipy dot optimize root. And this actually allows us to find the roots of our equation. All right, sweet. So we're going to type in from scipy dot optimize import root. So this actually allows us to find the import the root function and allows us to work with it below. So actually, let's go down here and let's put in, okay, our function which we're trying to solve for the roots for. So our pressure equation. And now we're going to throw in our initial guess. So let's put our initial guess. Our initial guess can be anything. Let's just throw in our initial temperature as our first guess. And let's run it. So as you can see here, it worked. So based on this right now, you can notice a couple of things about this. First of all, it says this negative number right here. It's very small. It's got like 9 zeros in front of it. And this is basically saying that here's our temperature, our final temperature we were solving for, is 366 degrees Kelvin. So basically what this is saying is when our final temperature is 366 degrees Kelvin, our function right here is going to go down to this value. It's going to go down as closely as possible to this value right here on a graph. And it says it took 15 guesses based on our guess of our initial temperature, being our guess here. It took 15 run-throughs of this this root function to get this value. All right, so this is actually the answer for what we're looking for. Our final temperature is 366 degrees Kelvin, given that the final pressure is 200,000 pascals. Okay, so now that we've solved the problem and found the final temperature of our first situation here, we're going to go on and move on to where we know two unknowns. In this case, we don't know the final temperature, and we are not given the initial total volume of the system which we were working in. But what we are given instead of that, we are given the desired amount of moles in the system, moles of air in the system, or vapor. Okay, So we can actually do this by using the same function, just copying it down here and manipulating this. So let's copy this and go down to a new. Let's do this, go down here. Now we go. Okay. So let's copy and paste this in here. And let's give it a new name. In this case, we'll give it the pressure equation 2. In this case, and we'll maybe give this a new name. This is where we do not know the, so unknowns are the total, in this case the volume total, and we do not know the final temperature. But we do know, in this case, we do know the number of moles, desired number of moles. It's 0.3. Okay? So now we know this. We already have this coded into where we do not know, we're solving for the final temperature. But now, since we have 2 unknowns, we need to actually add a second unknown. So let's see the V total. So we'll name it the same thing, VT, equals, in this case, the array that gives us the answer like before, X array, where this is the identifier of 0 is the first number in the array. We're going to name this the second number in the array as 1, and that'll be giving us our V total. So now we want to look down here at the V vapor phase. And actually what we're going to do, we're going to manipulate this equation here and actually solve for our V total with this. So in order to do this, we can actually take and, before we actually do this, let's go down here and add a new line. So the desired number, so let's say Wn underscore desired of moles, so number of moles of water desired is equal to 0.3. Okay? So we can actually go ahead and do this. We can take and subtract from the molar mass here. We can take and subtract the desired number of moles. So let's say Wn underscore desired. So desired number of moles. And let's see, we can multiply this by, so it's in moles right now. So you want to convert the number of moles that we have, that we're subtracting from the molar mass, which is 1 kilogram. And you want to multiply this by the molar mass of just water in general, which in this case we can find by doing P dot molecular weight. So MW. And then since the molar weight, we're going to have, if we did this right here, it would be in grams. So we want to make sure we divide by 1,000 to get it in kilograms, so all of our units are the same. So let's divide by 1,000. Okay. All right. Let's have that. Now, we can solve for the V total with this now. So now we want to actually solve for the number of, make sure we can solve for a number of moles here. Let's go down here. And we can actually solve for the number of moles, desired moles again, where we actually already know the desired number of moles. We can manipulate PV equals nRT to actually find this. So let's say the number of moles of water in the vapor phase, so Wn vapor, so in the vapor phase, equals the pressure of the water, which we already know, up here in the equation above, Pw, multiplied against the volume of the vapor, which we already know, divided by, in parentheses, R times the final temperature. All right, sweet. I think that's everything here. So something important to notice here, when we are solving, we have 2 unknowns. we want to make sure we have the same amount of equations that we are trying to set to 0 and find the roots for. So as of right now, we only have one equation. So we want to make sure we have two equations that we're solving for. So notice how I said before, we want to make sure that our equations are set to 0. So before we had the final pressure is equal to the partial pressure of air plus the partial pressure of water. So in order to set to 0, we subtracted the final pressure, which we know to be 200,000 pascals, and set it to the other side and set it equal to 0, so we could solve for it. So in this case, we want to do the same thing and set since we know that we want the desired number of moles, 0.03, to be equal to the number of moles of vapor, number of moles of water in the vapor phase. We want to set them equal to each other. So to set that equal to 0, we actually need to subtract the desired number of moles of water in the vapor phase to the other side and set it equal to 0. So we can actually do this by doing, let's see, so number of moles of water in the vapor phase, subtract the desired number of moles of water in the vapor phase. All right. Put that in brackets. All right. Shift enter. Shift enter here. So now we can go down and bring in a new line of code. And we can actually start solving for our roots. So root. Let's give our initial guesses. So for this instance, our guesses for temperature and for our total volume. So I'm actually going to use my initial guess for temperature. We can use anything. And we might have to put in other guesses. Sometimes our guesses are wrong, so we have to use multiple guesses. So for my first guess, I think I'm going to try to use something close to the final temperature we had last time, where we knew the total volume, but we didn't know the final temperature. So I'm going to put something close to that, put like 360, and see if that works. So 360 degrees Kelvin is going to be my initial guess for temperature, final temperature. And for the desired number of moles, I'm going to guess somewhere, let's guess something like 0.1 moles. All right. So, oh yeah, and I forgot something. We need to make sure that we put our equation in. I would have gotten an error there. Okay. So, pressure equation 2. And now I need to do 2 brackets there. Let's run it. Okay, so it says here I got an error, it did not work. It said the iteration did not make good progress. So that means my guess was off in some way. So we can start manipulating the equations around here, our guesses, and see if we get something closer. So it did run, but it did not make good progress. So let's try a different number for our volume. Yes. Something went wrong here. Let's see. So, okay, so I think I see the problem here. So you can see here where my parentheses are off. And parentheses can mean a lot of things. They can change up a lot of the equation. And if they aren't in the right place, you're not going to get right answers. So let's give it a run. And yeah. All right, sweet. So it says here that our solution converged. That means that it passes it over the x-axis in this case and gave us our zeros. It says right here it took about 18 runs with the initial guesses we have here. It took 18 iterations to get the answers that we have. So it was a success. And it says here that our final temperature in Kelvin is going to be 325.9 degrees Kelvin. And our number of moles is actually going to be, let's see, it's going to be 0.05 moles. 1, 2, yep, 0.05 moles. Or not 0.05 moles, sorry. It's going to be not the number of moles, it's going to be the total volume. My bad. Total volume is going to be 0.05 meters cubed. All right, sweet. And our final temperature, like I said, was 325.9 degrees Kelvin. All right, thank you so much for watching in this example of how to solve for the total volume and in the solve for the final temperature in two different equations.